Hello, and welcome to week number 10, BC Calculus. Let's begin. Last week we were talking about linearization and L'Hopital's rule. Linearization, as we went over, just basically is the same thing as finding an equation of a tangent line. So if I wanted to find what is the linearization of f of x equals e to the x at x equals 1, still, I'm just going to find, just like I do with a tangent line, I need to find the point and slope. Well, the point for this problem, we already know the x value is 1. If I plug 1 in here, e to the first is just e. So there's my point. If I need the slope, I just take the derivative of e to the x, which is e to the x. If I put 1 in here, this gives me e for my slope also. So my equation is y minus e is equal to e x minus 1. Well, it doesn't look like any of them up here, but let's try to rewrite this thing. If I do, I can add an e to both sides. Let's see here. Or I can multiply through here. So I've got e to the x minus e. And if I add an e to both sides, that just gives me e times x for my answer. Then we also talked about finding the limits using L'Hopital's formula. So L'Hopital's formula says that if we put a value in and we end up with 0 on top and 0 on bottom, we can use L'Hopital's formula to find the limit. So in this problem, if I took the derivative of the top, I end up with negative 4x. I think there's supposed to be a x here, but I'm just just thinking it must. Well, maybe it's not. And then that would just be 4x on top, and on the bottom it would just be a 1. Put the 8 in there now, end up with negative 32. So using L'Hopital's formula to find derivatives or finding limits is pretty easy. All we're doing is we're taking the derivative top and bottom. If I put 0 in here, for this would be the sine of 0, which is 0. Put 0 in here, I get 0. So now I take the derivative. Sine of 2x is going to be cosine 2x times 2 all over the derivative of x is just 1. Now if I put 0 in here, the cosine of 0 is 1. I have a 2 on the outside, so that's 2 over 1, which is just 2. And that was the last of the reviews. Okay, let's see here. I think somebody came in here. Caleb, how are you doing today? Nope, you probably don't have any. Let me turn on the settings here. That's not it. All right, that should do it. How are you doing today, Caleb?
There we go. Hey, I'm doing good. Can you hear me?
All right, this week we're going to work on the mean value theorem, finding critical points, and the biggie is the first derivative test. All right, sounds great. All right, so a lot of today's work deals with finding maximums and minimums, local max, local min, absolute max, absolute min. When we take a derivative and we set it equal to 0, we end up finding where the max and mins are of functions. And they are important. The absolute extreme values, an absolute maximum on D is if there's no point around it that is any higher than it. That's basically a max. Absolute min. Now, an absolute or global max and min values are also called absolute extreme. We often omit the term absolute or global and just say a max and min. The extreme values can occur almost anywhere. For example, in the first diagram, this would be a maximum value, this would be a minimum value. So my max and mins can occur inside the function. On this one, my maximum occurs at the left-hand side, minimum occurs at the right-hand side. So max and mins can also occur at the endpoints. That's why when we're finding max and mins, we always look at the endpoints because the endpoints can be solutions. In this problem, I have a minimum at an endpoint and a maximum inside the function. And then this one, I have a minimum inside the function and a maximum at the endpoint. So endpoints are, the big takeaway is that you do have to check endpoints for max and mins. Now, some books use local max and mins, some use absolute max and mins. A local is a max that is not higher than what we call the absolute max. So this point here is the very highest, so we call that an absolute max. And this one isn't as high as the absolute, so we call it a local maximum. This is a local min, this is a local min, this is an absolute min because there's no point on the graph that is any lower than it. So we call it an absolute. Max and mins are extreme values. We call them max and mins. In order to find an extreme value or a max and min, we take the derivative, set it equal to 0, and solve. In this is one of those Khan Academy questions. It says over the region 1 to 3, the point B is. Well, now they call them global max, and so some books call absolute and some books call them global. So in this problem, I would say that this is a global minimum because it is the lowest point. There is no other point that is any lower. So we could call it an absolute or a global minimum. In this problem here, it says over the region shown, there are local minima at the points. Well, there's a local min at C. These would be local maxes. Now somebody would say, well, isn't this a local min? No, that would be an absolute min because it is the lowest point on the graph. On this problem, it should say x equals 0 to 3. The point C is, well, I would say that that is a local min because it's lower than any point around it, but it is not the lowest point on the graph. So the difference between local and absolutes. What is the average rate of change between the points? Now, this gets into a little bit different type of problem, but a local or the average rate of change is the distance, or it is the slope of the endpoints. Okay, so this endpoint here is 0, 0. This endpoint here looks like it's 4, 4. So if I wanted to find the slope, I'd go 4 minus 0 over 4 minus 0, which is 4 over 4, which is 1. So the average rate of change between A and B would be 1. And then it's just finding the slope. Find the value of the derivative, if it exists, of the function f of x equals 11 minus the absolute value of x. Okay, so this is the graph of it. Okay. And it says find the value of the derivative at the point 0, 1. Or I'm sorry, 0, 11. So I would say that it does not exist. The reason it doesn't exist, there's a corner there. A derivative does not occur when there's a corner, a cusp, or a vertical tangent line there. So it does not exist. All right. Now I'm going to let you do a little bit of work. Caleb, this one it says sketch the graph. Now you don't have to sketch the graph for this problem. I mean, you could if you wanted to. And then it says and locate the absolute extreme of the functions on the interval from 0 to 6. Okay, so what I want you to do is I want you to find the absolute extreme on the so the absolute max and absolute min on the interval from 0 to 6. Okay, so I'm going to let you try that and see what you get. Or D? Okay. So if I was going to do this problem, first thing I would do, I'd plug, no, I might graph it. Negative 32 and 16x. Well, that means this thing starts way down here, negative 32, but the slope is 16x, so it looks like it's going to be a positive 32, isn't it, at 4? So this point here, 432, okay, and then 2x squared between 4 and 6. Okay, well, if I put 4 in here, this is going to be 32, so that means this graph is going to start going to look like that. Okay, so I've got two graphs that they touch each other, so this is the second graph. Okay, and it goes all the way up to 6, so if I put 6 in here, 6 squared is 36 times, so this point here would be 672, I believe. So B, whoops. So my absolute min is going to be 0, negative 32, and my absolute max is going to be 672. So let's see here, 0, negative 32, and 672. I'm going to go with letter E on that one. Does that make sense? Absolute min, absolute max. I'm graphing out the function. I didn't need to graph it out because I could have just put in the values. I could have put 0 in here, could have put 4 in here, could have put 4 in here and 6 in here, and I would have came up with the same values. All right, the mean value theorem. The mean value theorem says if f is continuous on a closed interval a and b and differentiable on an open interval a to b, then there exists a number c in AB such that f prime of c is equal to f of b minus f of a over b minus a. Whew. Ooh, that's a lot of gobbledygook. Basically what it's saying is if I have a function, okay, let me draw out a graph here. Let's just use a really simple one. Let's just say that I have y is equal to x squared. So we know that that graph looks something like this. And I was going to say, okay, on an interval from 0 to 4, okay, find the value of c. Well, what that's saying is, if you draw a secant line at the endpoints, okay, 0, 4, that's my interval, 0, 4. So this is 0, 0. And if I go all the way out to 4 here on the x-axis, and if I put 4 in here, 4 squared is 16, so that would be 416. So what they're saying is, if I draw a secant line, okay, so this is a secant line. The green one is the secant line. And the slope of this secant line, I can figure out that. So that's 16 minus 0 over 4 minus 0. So that secant line has a slope of 4. What the mean value theorem is saying is, hey, there is a point someplace between 0 and 4 on the interval 0 to 4. So there is a point someplace on this graph that when I draw the secant, or when I draw the tangent line, it is going to be parallel to the secant line. It's going to have the exact same slope as the secant line. Okay, so what I'm trying to do is I'm trying to find that point C. Well, it's pretty easy. We know what the slope is. All we have to do is take the derivative of my function. So the derivative of x squared is 2x. Set it equal to 4, because that's the slope of the secant line. Solve for x, so x equals 2. So I know when x equals 2, the slope of the tangent line will equal the slope of the secant line. That is basically what the mean value theorem says. It says that if you draw a secant line in there, the slope of the secant line will equal the slope of the tangent line at some point C. Okay, fairly easy to understand. So here, oops, I don't know why those are the same. Okay, so in this problem, it says show that the function, let me see if I have a different problem because that one's way closer, very done much better than mine. Okay, so this one right here. It says find the value of c that satisfies the mean value theorem for f of x equals 3x squared plus 5x minus 2 on the interval from -1 to 1. All right, Caleb, this is your problem. All right, I want you to find the value of c that makes the mean value theorem true. Right? You don't get this concept. And how do I know that? Because your answer, any number between -4 and 6, can't be. The number has to be, the value c has to be someplace in your interval. I know that my answer has to be between -1 and 1. That's it. So now let's graph this out. 3x squared plus 5x minus 2. I don't have a clue what it graphs out to be. It really doesn't matter. Let's just say it graphs out like this. Okay? So what we need to do is we need to find the endpoints. What is f of -1? What is f of 1? Those are our endpoints. -1 is, I don't know where -1 is because I don't know if this graph is very good. So let's just put -1 in here. -1 squared is 1, so this becomes 3 plus -5 minus 2. So that's -7 plus 3, that's -4. So let's say that this is -1 here. So this point right here is -1 comma, what did I say it was? -4? All right. And then I have to find where 1 is. Okay, so that's -4. So I'm going to plug 1 in here. So if I plug 1 in here, I end up with 3 again, plus 5 minus 2, so that's 8 minus 2, that's 6. Okay, so at 1, let's say 1 is here, it's at 6, 1 comma 6. Okay, so that's the first step you always do. Second step, you draw a secant line between your endpoints. There's my secant line. A secant line is not a tangent line. A secant line cuts the graph in two places. What is the slope of the secant line? That is my next step. So I need to find the slope of the secant line. Well, 6 minus 4 over 1 minus -1. So that is 2 over 2. So the slope of this secant line is 1. Now what the mean value theorem says, it says that on the interval between -1 and 1, there is going to be a point someplace on the graph that if you draw a tangent line, it is going to be parallel to the secant line. Okay, well, if they're parallel, what do I know about the slope of that blue line? What does it have to be? Okay, so if I know that the secant line and the tangent line have to have the same slope, in this problem, the slope of the secant line was 1, so I know the slope of this line also has to be 1. Okay, so now, how do I find the value of c between -1 and 1? Well, guess what? You take the derivative of this thing and you set it equal to the slope. So if I take the derivative of this, that gives me 6x plus 5 is equal to 1, because that is the slope. So if I solve this, 6x equals -4. Divide through by 6. I end up with -4/6, which is -2/3. Is -2/3 in my interval between -1 and 1? You think the slope should be 5? All right. -1 plus, that's 2, isn't it? 6. All right. This isn't a 4 here. This is, oh, it is a 4. Oh, I thought that was a 1. I'm sorry. All right. So on top, I have 6 minus -4. Okay. Sorry about that. It looked like a 1 to me. And then 1 minus -1. So that gives me 10/2. Oh, so the slope is 5. Okay. So now I take the derivative and I set it equal to my slope. Makes a little bit more sense. If I subtract off 5 here, I end up with 6x equals 0, x equals 0. So is my c value in my interval? Yeah, 0 is in between -1 and 1. Does that make sense? You think so? You want to go through another one? I don't know if I have another one. No, I don't. But let me just make one up. All right. Let's say my function is 4x squared minus 5, and I want my interval to be 0 to 3. Okay. What is the c value? Now, 3/2 sounds like a much nicer answer than what you gave me before. No, I don't know. I didn't do the problem, and it's probably not a really nice problem because I just made the numbers up. But 4x squared minus 5, I know what that graph looks like. It's down at -5, and it goes like this. So I'm going from 0 to 3. So the next thing I do is I put 0 here. Well, this value is 0, -5, if my math is correct. And then I go over to 3, and I find my value there. If I plug 3 in here, 3 squared is 9. 4 times 9 is 36. 36 minus 5 is 31. Okay, so now I have to find the slope. See if I can find it correctly this time. 31 minus a -5 over 3 minus 0. So my slope is 36 over 3. Oh, that didn't turn out too bad. So my slope is 12. Is that right? So my slope is 12. So now I need to find a value of c that when I draw the tangent line in, it's parallel to the secant line. Well, if it's parallel to the secant line, I know the slope has to be 12. Well, if I take the derivative of this and set it equal to 12, that's my c value. So Let's see here, 4x squared, that's going to give me 8x equals 12. Divide through by 8. I end up with x equals 3/2. You are absolutely correct. All right, so that's how you find the C value for the mean value theorem. The rest of the hour, we're going to talk about the first derivative test. Next week, we're going to talk about the second derivative test. The first derivative test gives us max and mins. It also tells us where the function is increasing and decreasing. Do you remember the first and second derivative test from last year, Caleb? Okay. So now, let's just go to a problem. Right. So this is what I expect students to be able to do. Given a function, you're going to use what is called the first derivative test. Okay, so the first derivative test, what you want to do is you want to set up a table. So take that back. This is my first derivative. So this is my first derivative test. So you want to take the first derivative. Okay, so if I take the derivative here, I get 3x squared minus 12, and you want to set that equal to 0 because you want to find the intervals for where your first derivative is set equal to 0. Why? Because this is where you have max and mins. This is where the graph is changing directions. Okay, so I'm going to set this equal to 0. So 3x squared minus 12 equals 0. Bring the 12 over. 3x squared equals 12. Divide through by 3x squared equals 4. Take the square root of both sides. X equals plus or minus 2. So now I know that I have on my intervals. Okay, and sometimes when I first start teaching kids this in AB Calc, I always have them set up a number line. So my answers are -2 and 2. So what are my intervals? Well, this side is a negative infinity, this side's positive infinity. So I have an interval from negative infinity to -2. I also have an interval from -2 to positive 2. And my last interval is from 2 to infinity. So those are my intervals. Now, what we want to do is we want to find out where they're positive and negative. Okay, so all I'm going to do is I'm going to put a value back into my derivative. That's why it's called the first derivative test. So I've got 3x squared minus 12. I'm going to put a value here in this interval from negative infinity to -2. So let's try -10. So if I put -10 in here, all I care about is it positive or negative. So if I put -10 in here, -10 squared is 100, is 100. 3 times 100 is 300. 300 minus 12, that's definitely positive. So I know my function from negative infinity to -2, my function is increasing. That's what a positive tells us. It's increasing. So from -2 to 2, I'm going to use the value 0. I can use any value in this interval. So I'm going to use 0. So I put 0 in here. 3 times 0 squared is 0 minus 12. That's definitely negative. So I know my function is decreasing at -2, between -2 and 2. And then at the very last one, let's put 10 in here. So if I put 10, this is definitely going to be positive. So I know my function is increasing here. Now, if a function is increasing and then it decreases, there is a maximum. So I know there is a max at x equals -2. Then it decreases and starts to increase. So I know there has to be a minimum at x equals 2. So the first derivative test tells us where a function is increasing or decreasing. It also tells me where a function's max and min values are. That is what the first derivative test gives us. Okay? Gives us where it's increasing or decreasing. It also tells us if there's a max or a min at any of the values. That is the first derivative test. Next week we'll be talking second derivative test. Second derivative test gives us concavity. Where is a function concave up, concave down, and it also gives us critical points. Okay? All right. Hopefully we have another. All right. So this problem right here, I am going to let you work a little while. I'm going to ask you to find where is this function increasing, where is it decreasing. I want you to find all of the max and mins. Okay? So this one is up to you. I'm going to turn off my mic and I'm going to let you work for a couple minutes. and see if you can find all that. Now, you can do your work on the board if you want to, or I can work it out after I come back. All right, so take some time, work on this, and see what you get. All right, what did you find the values to be for your intervals? So I think that's probably the hardest thing to do is find the intervals that you're looking at. What intervals did you get, Caleb?
I got -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. So zeros at -1, 0, and 1.
Okay, and I'm gonna start doing the work up here. So to find my intervals, first thing I have to do is I have to find the derivative and then set it equal to 0. So my derivative here is going to be 8x to the third minus 8x. Okay, so now I have to set it equal to 0. Well, I've always learned to factor out the greatest common factor, so I'm going to factor out an 8x. So that leaves me with x squared minus 1. Well, so this becomes 8x, x minus 1, x plus 1. So I know that I have a value of 0. My solutions are 0, 1, and -1. Those are my solutions. So if I set up a number line, I just put those on there, -1, 0, 1. This is negative infinity. And this is positive infinity. So my intervals in this problem are going to be from negative infinity to -1, from -1 to 0, from 0 to 1, and 1 to infinity. Those are my intervals. Now I have to try every value in here. Okay, so I always use my factored form when I'm doing this, because then all I need to know is positive and negative. And I'll show you what I mean in just a second. Okay, so if between negative infinity and -1, let's try -10. Okay, so if I put -10 in here, 8 times -10, that's negative. -10 minus 1, that's negative. -10 plus 1, that's negative. So negative times negative times negative is negative. This is negative here. It's all I needed to know, because now I know it is decreasing there. From -1 to 0, there's not a lot of values that I can use. I'll use -1/2. So if I put -1/2 in here, 8 times -1/2, that's negative. -1/2 minus 1, that's negative. -1/2 plus 1, that's positive. So negative times positive, that is positive. I know this function is increasing here. Let's try positive 1/2. That's going to be positive, negative, positive. Well, positive, negative, positive, that is definitely negative. And then my last one is going to be positive. So decrease, increase. So there's my there's my table. Now my table is going to tell me a lot. It tells me where my function's increasing, decreasing. It also tells me max and mins. So if it decreases and increases, I know at x equals -1, there is a min. Then it increases and decreases, so I know at x equals 0, max. I know that decreasing, so x equals 1 is a min. And then it's going to turn and continue going up the rest of the time. And I see that you already have local min at -1 and 1, and local max at 0. Very nice. That is the first derivative test. Any questions, Caleb?
I do actually have a question. So since the graph is decreasing from large negative numbers and increasing for all positive numbers, it's making kind of a W, right?
That was the last slide for today. Next week, we will be talking about second derivative test, which gives us concavity and critical points. All right, Caleb, you have a great evening and rest of the week. Absolute, I don't think so, because you can tell that this function is going to look something like this. If I graph this function out, okay, I know at -1 it has a min. I know at 0 it has a max, and I'm just guessing at where they go. This has a min, but I do know that the function is decreasing, then it increases, then it decreases, and then it increases. So my graph is going to look like a W. So these are what we would call local, because in absolute, this function keeps going. So the absolute would have to be out here someplace. So we would just consider them local max and local mins, because they are, but I would say that is an absolute min though. Well, I don't know which one is an absolute min, but I have a feeling they both go down to the same value. But yeah, I would assume that they're both absolute mins here, because it looks like they probably go, because it doesn't go any farther down, right? Yeah, if they equal the same thing, then yes, those would be considered absolute mins, because that graph is never going any lower than that. Correct. Yes, they would both be absolute, and then that maximum would be a local max, because the function does go farther up, just not there at 0. Any other questions? All right, Caleb, you have a great week. Try to stay warm, because it's supposed to get colder this week. Bye.